The last lecture we discussed about the DC equivalent circuit and DC load line of a common emitter transistor amplifier. Now in this lecture we will discuss about the AC equivalent circuit of a common emitter transistor amplifier. So to consider an AC equivalent circuit, we have to do two things. That is, we have to remove the DC sources in the circuit. In this circuit, plus VCC is the DC source, and also we have to consider the capacitor, which since the capacitor allows AC and does not allow DC, or ideally we can speak a capacitor offers zero reactance to AC signal and it blocks DC. We have to short all the capacitors in the circuit when we are considering the AC conditions. So first step is remove all DC sources. Then second step, since for AC the capacitor offers negligible reactance, ideally we can say that it offers zero reactance to AC. So short all capacitor. Short means replace the capacitor and connect that two terminals by a wire. Then shorting the capacitor is the another step we have to take. So if we consider this one, then when we remove VCC, then RC will be at a potential 0, that means it should be grounded, and R1 is also at a potential 0, that means it should also be grounded. And we have to short the C in input capacitor, that means we have to connect a wire like this and remove this capacitor. Similarly here we have to remove this capacitor C and short this terminal. That means there is no current flowing through RE, so there is no RE in the picture when we short this emitter terminals. And remove this coupling capacitor CC and connect by a wire to RL. So the resulting picture of the AC equivalent circuit of a common emitter transistor amplifier will be in this one as shown in this diagram. That is, one end of the R1 is connected to base and other end is shorted. One end of the R2 is also connected to base and other end is grounded. Here R1 is also grounded, sorry for using shorted. And also the emitter terminal is shorted, that means removed, there is no current through the RE, so we can remove that RE and we can ground the emitter directly. And across RC, one end of the RC is connected to the collector terminal and other end is grounded, and RL is also, one end is already grounded and other end is connected to the collector, since we are shorted the coupling capacitor CC. And this is the AC equivalent of a circuit of a common emitter transistor amplifier. Now from here we can calculate the different currents. That is, the current IB is the base current, which is purely AC, and which is given by actually the input voltage V in is equal to IB into R in. R in is actually the effective resistance of R1, R2 and the input resistance of this base emitter junction, and the output resistance is actually output current is IC, and the emitter current is IE. The output resistance, actually we call it as the AC load. Similar to the case of a DC load, we are having an AC load here, and here we can see that the AC load is the parallel combination of RC and RL. So the AC load is given by RC parallel to RL. That means it is equal to RC into RL divided by RC plus RL is the AC load of the AC equivalent circuit of a common emitter transistor amplifier, or the AC load of the common emitter transistor amplifier, RC parallel to RL. Now the quantities which we can obtain from here is that when the signal is applied, then the maximum collector current due to signal is maximum collector current due to signal. I can call it as due to signal, we are representing it by small IC, and the maximum value of this one is equal to IC because for the faithful amplification. If this IC exceeds the zero signal collector current, that is capital IC, then we know that there is no faithful amplification. So to occur faithful amplification, the maximum value of the collector current due to signal alone will be equal to the zero signal collector current. So we can say that IC, small IC max is equal to IC, the zero signal collector current. Then we have already obtained the AC load as, we denote it by RAC, which is equal to RC parallel to RL, or the actual value will be RC into RL divided by RC plus RL. So then if this is the maximum collector current due to signal, then we can obtain the expression for the maximum positive swing for the or of AC collector emitter voltage is equal to, that is maximum positive swing of AC collector emitter voltage means it is the maximum collector emitter voltage due to the signal is the maximum collector current due to the signal into the resistance, that is RAC. IC into RAC gives the maximum positive swing of AC collector emitter voltage. Then we can write the expression for maximum or total maximum collector emitter voltage as that is usually the total collector emitter voltage is the sum of the AC collector emitter voltage and DC collector emitter voltage. The maximum value of this quantity will be equal to the zero signal collector emitter voltage plus the maximum swing of the collector AC collector emitter voltage, that is IC into RAC. So this is a very important expression in the case of a common emitter transistor amplifier. The maximum collector emitter voltage is given by VCE plus IC RAC, where VCE is the zero signal collector emitter voltage or the collector emitter voltage due to the DC condition, and IC is the zero signal collector current, and RAC is the AC load resistance of the circuit. Then similarly we can obtain the maximum positive swing of AC collector current in terms of the VCE as VCE divided by RAC. So the total maximum collector current is given by that is IC max is given by the sum of the DC collector current plus the maximum swing of the collector current due to signal, that is VCE by RAC. So this is another quantity in the case of a common emitter transistor amplifier. So the maximum collector emitter voltage when signal is applied, this is the maximum collector current when signal is applied. The first two terms are in those two expressions is due to the DC, and second expressions is due to the maximum values due to AC signal. Now let's discuss about the AC load line, because we have discussed that output voltage and current are due to the sum of the AC voltages and DC AC quantities and DC quantities. We have discussed the DC quantities, that is DC collector current and DC collector emitter voltage. Now let's see the variation or the relation between the collector current and collector emitter voltage when signal is applied, and which is called the AC load line. So AC load line means it is the line on the output characteristics of a transistor circuit, which gives the values of IC and VCE when signal is applied. So when signal is applied, we know that VCC is equal to ICRC plus VCE, or VCE is equal to VCC minus ICRC. Again, this VCE and IC, dependence of IC are a linear relation, and that can be plotted in the output characteristics as a straight line. The two endpoints are given by C and D, where the point C represents the maximum value of the point C is actually represents the maximum value of collector emitter voltage when signal is applied, that we have already obtained in the previous that VCE maximum is VCE plus IC into RAC. So this maximum value of VC collector emitter voltage is given by VCE plus IC into RAC. So that is the one end of this AC load line C on the x-axis. So this is VCE plus IC into RAC, maximum value of VCE, and the maximum value of the other point D is the maximum value of the collector current which is obtained earlier, that this maximum value is equal to IC plus VCE divided by RAC. So from these two expressions we can determine the two endpoints C and D of the AC load line. This is the AC load line where the RAC is given by the effective AC load resistance, which is equal to RC parallel to RL, and from in this way we can determine the AC load line of a transistor. Okay, thank you.